Today I'll be solving a problem, and the problem is water is pumped from the large tank shown in diagram A. This is diagram A. Below, the entrance to the pipe section is sharp edged and the pipe is cast iron with a total length of 2 meters. Flow within the pipe is observed to be fully turbulent. The relationship between volumetric flow rate and the actual head rate is provided in the pump specifications and showed in diagram B. And today we're asked to determine the volumetric flow rate for this system and show that the observation of fully turbulent flow was correct. And if the pump is 70% efficient, determine how much power must be supplied to the pump. Okay, so to start off this equation or problem, I like to write down the givens. So L in this case is 2.0 meters. The diameter is 0.07 meters. And in this case, we'll say Z1 minus Z2 is 6 meters because of this right here. So to start with this problem, we would use energy equation, and it is P1 over gamma plus V1 squared over 2G plus Z1 plus HP equal to P2 over gamma plus V2 squared over 2G plus Z2 plus head loss. So we can eliminate some variables in this equation since it's opening to the atmosphere. So then P1, P2 is the same thing. So it'd be atmospheric pressure, so that cancels out. And there's no velocity at 1, so this would be 0. So then that would cancel out too. So now we're left with this equation. So let me rewrite it. It'd be Z1 minus Z2 plus HP equals to V squared over V2 squared 2G plus Z2, or not Z2 because we moved it, plus head loss. So head loss would be your FL over D V squared over 2G plus K V squared over 2G. Then to plug in everything and plug in HP, HP is given in the problem. So HP is 20 minus 2000 Q squared. So to plug in that Z1 minus Z2, it's 6 plus 20 minus 2000 Q squared equal to V, so we'll say V squared over 2 times 9.81 plus F, then L is 2 over 0.07 V squared over 2 times 9.81 plus K in this case would be the minor loss coefficient because of the sharp edge. So then it would be 0.5 V squared over 2 times 9.81. And in order to solve or to further solve this equation to get F, or get V, my bad, we would need to find Q. So Q, volumetric flow rate, equal to pi over 4 d squared V. So then in this case, Q, you would equal pi over 4 times 0.07 squared V. And Q equals, let me do calculations, pi divided by 4 times 0.07 squared equal to 0.003848 V. Since we don't know what V is, then we plug this Q back into the equation. So it'd be, simplify more, 26 plus Oh, so it would be minus, my bad. So that's 26 minus 2,000 times this squared. So then that would be 2,000 times 0.003848 squared. And that ultimately equal to 0.0296 v squared equal to, so then this one would be 1 divided by 2 divided by 9.1. That would be 0.0510 v squared plus 2 divided by 0.07 divided by 9.1 divided by 2. That would be 1.456 f v squared. Then the last one would be 0.5 divided by 2 divided by 9.81. And that would be plus 0.025 v squared. And ultimately, to simplify this equation to get v by itself, it would be 26 equal to, so let's see, 0.0510 plus 0.0255 plus 0.0296 would equal to 0.106 v squared plus 1.456 v squared f. So then to manipulate it to get v by 0 would be v equal to square root 26 over 0.106 plus 1.456 f. We got that because you pull out v squared, then you divide 0.106 plus 0.456 f divided by 26 divided by that, and you square root it, and that's how you get your v. And in order to find the f, we would utilize another equation in this case, and the equation would be the Colebrook equation, and that equation would equal 1 over square root f equal to negative 2 log parentheses epsilon over 3.7d plus 2.51 over re square root f. And sorry, my pen's bugging right now. So, okay. So in order to solve this equation 2, we would need to find Reynolds number. So RE is equal to rho VD over mu. In this case, rho is 999. Then V, we don't know V. Then density is 0.07. And the dynamic viscosity of water, I think so, yeah, is 1.12 times 10 to the negative 3. Ultimate RE would equal to 9 times 0.07 divided by 0.12 times 10 to the negative 3. It's 62437.5 V, since we don't know what V is. Then after that, we would plug RE back into this equation. So 1 over square root f equals negative 2 log epsilon. In this case would be 0.002. Oh, my bad, another 0.026 over 3.7. D is 0.07 plus, and this can be a long equation because you need to plug in RE, then V2 because V is right there. So then it would be 62437.5 times your square root of 26 over 0.106 plus 1.456 f, then times f, over 2.51, then that parentheses. So after that, the f would be based on I would oh sorry, I can't see it. I would refer to the Moody diagram. Then to look at my range for f, then based on the surface roughness and fully determinant, it was approximated to be, and using the online calculator, it was approximated to be f equals 0.026. Then after, we would use this f found to plug back into our v in order to find our v equation. So I'll flip back and forth. So let me see if you can see it. V, oh, whoops, almost not with the camera. V equals square root of, let me flip back, 26 over 0.106 plus 1.456f. So then f was 0.026. We'll plug in f. Let me calculate it. So screw it. 26 divided by 0.106 plus 1.456 times 0.026, and then velocity would be 13.44 meters per second. Then after that, we would use our v to find our q, which is part A. Q equals, since we solved for q already, and all we knew is v, it was 0.0034848v. So then we plug this v into this. So then our volumetric flow rate for part A would be 0.003848 times 13.44. Ultimately, our volumetric flow would be 0.517 meters cubed. So that's part A. Then part B, we were asked to show that the observation of fully determinate flow was correct, and in order to do that, we would use Reynolds number equals, and since we haven't given that, it's 62375. All right. Look, use the wrong one. My number, it's 62437.5 times your v. So then you use the v again over here. So RE is equal to 62437.5 times 13.44. Then RU would equal 839160. And since that number is greater than 4,000, it concludes that it is fully turbulent. All right, then the last part, part C, you were given that the pump, if the pump is at efficiency, so N equals 70% or 0.7, what would the power be supplied to the pump? So, let me move this up. P, or power, is equal to PG HQ over efficiency. But then we don't know what H is, so we'll use H in this case, since that was given HP, is equal to 20 minus 2000 Q squared. Plug in our values, use that Q, this one, to right here. So H would be ultimately equal to times 0.517 Oh, I think I missed the 0 up here for volumetric flow rate because it's, oh yeah, I did. So this is 0. So that's where I could have went wrong. So let me plug that back into it. 20 minus 2000 times 0.0517 squared. And ultimately I would get 14.65. Then I would use this to plug back in here. And since we know all our other givens, P equals to 999 times 9.81 times 14.65 times Q, which we found already, 0.0517 over 0.7, and power is ultimately times 14.65 times 0.0517 divided by 0.7 is 10,603 watts, but then you want to make it look cleaner, divided by 1,000, P is equal to 10.60 kilowatt. And that's our answer for C. Thank you, and I am Justin Legaspi. My rate ID is 8231999020, and this is my signature. Thank you.